Greetings. In this one, I will be focused on this system of two linear equations. And the point is, of course, this can be solved in simple algebraic way. But the focus of this video is to describe the possibility to use the inverse of a matrix. All right, so a coefficient carrying matrix of columns to take the advantage of the properties of a matrix and its inverse in order to solve such a thing. And in order to do that, I will use some rules that will be applicable and especially visible once I translate this expression into a more matrix looking one. Alright, so how this can be translated into a matrix is basically on the left side, I take the coefficients. Well, I see the x1s are on the first place above each other. The x2 is like this, so it's 2, 3. And then here it's for x2, it's 1 and 5. There's the coefficients. And of course, these are just coefficients now. And in order not to lose this information x1, x2, I will multiply this matrix carrying these coefficients by this vector x1, x2. And what this means is this can backwards get multiplied out. The x1 will apply to this column, the x2 will apply to this column. And so if it gets written out again, it will indeed give these two rows. And on the right side is equal to these two numbers in a vector as follows. Alright, so this is basically the ax equals b notation is the equation with a matrix, a vector equal to this vector and so on. And so the point of this video is in order for us to be able to solve it, not using an augmented matrix necessarily, but instead use the matrix itself and just look at these coefficients. And by being able to take the inverse, and in this case it's a 2 by 2 matrix, a very easy one to take the inverse of. And by taking the inverse, to use this property of the inverse in order to solve it. So the basic idea here is that one can use the inverse to move around the matrix from the left side to the right side and the other way around. And the point is that here is this matrix 2, 1, 3, 5. Here is the x1, x2, and here is 7, 2 vector, right? And the solution to this equation will be this vector. Namely, we want to evaluate x1 and x2. How is that going to happen? Is by getting this matrix to the right side. In case I want to solve it through the method as I mentioned, using the inverse, which is exactly what I'm doing here. So the point of this approach is that I want to get x1, x2 separated on one side by itself, namely I will leave it on the left side, and I want to move this matrix to the right side together towards this vector here. So how it will end up is x1, x2 on the left side as follows, and then on the right side is 7, 2, and it gets multiplied by something, or divided, right? Usually in algebra, if this is multiplied by this, well, that would mean that I would do 1 over this matrix. But the way to do this in matrix algebra is basically by multiplying both sides by the inverse of this matrix. Alright, so by multiplying both sides by the inverse of this matrix, it can be eliminated from here, because multiplying this by its inverse will give the identity matrix of the same amount of entries, and that basically is like if there was nothing, because it will leave this vector as is, it won't transform it in any particular way. It will keep its coefficient same. And so this will kind of disappear on the left side. And then on the right side will appear, well, both sides have to be multiplied by the same thing. So on the other side will appear the inverse of this. So in order to get, right now this is the first step, this is the first form. Basically it's still the same thing as was here in the beginning. But in order to get this by itself on the left side, leave it there, and get this to the right side, I can multiply both sides of this equation by the inverse of this matrix. So I will multiply both sides by the inverse, or multiply both sides by the inverse of this matrix. So on the left side, well, multiplying matrix by its own inverse gives the identity matrix, and I didn't even have to write it because it will just keep it the same way. Like this is not even there really. And this of course has to be applied to both sides, so the 7, 2 will be multiplied by the inverse of this. And namely, how to get the inverse of it in a second I will show. Alright, inverse denoted as to the minus 1. That's the notation for an inverse of a matrix. Of course, if I had matrix A, then the inverse will be A to the minus 1. That would be the notation in general for them. Alright, so this is basically the situation right now. And now by using, let's say, vector multiplication over a matrix, or multiplication of this simple matrix and this vector, well, x1 applies to this column, x2 applies to this column, so it's 1, 0 plus x2 times 0, 1. And what this means is x1, x2 is the result. So when I multiply this vector by this 1, 0, 0, 1 identity matrix, which is the result of multiplying this matrix by its own inverse, then it really is no effect on it. It's the same like multiplying this by constant term 1. Therefore, this didn't really have to be written as I said. It was just a systematic thing to just make sure it's shown, but it's not definitely. In practical terms, definitely in quicker steps, one would simply do this. I would multiply both sides by the inverse of this. This disappears on the left side, and it's and the inverse by which both sides are multiplied appears, of course, here. Alright, so what I have now is this vector times the inverse of this matrix. And the inverse of this matrix will still be a 4-entry matrix, but in order to take the inverse of a 2x2 matrix, there are some rules that I used in the previous video because there has been one on how to take the inverse of a 2x2 matrix, and the rules are very straightforward. It's very easy to do it. So the inverse of such a matrix is basically I might already replace it right here. Instead of writing another line, I can just delete this notation, I can write the inverse. So the inverse of this matrix, basically right now it's not the inverse yet, but the inverse is done as follows. These two diagonal terms, so the left top one and the bottom right one, are switched. That means 5 goes here, 2 goes here. And these two diagonal terms, the left bottom one and the top right one, are multiplied by minus 1. And that's it. That's how one gets the inverse. Alright, so the inverse notation no longer needed because it became the inverse. Alright, so this is it basically. When one knows how to take the inverse of a matrix, one is able to just get it to the other side, and now I have the direct expression for x1 and x2, and that is the goal of this process. So x1, x2 will equal to this. And again, how to multiply this vector by this matrix? Well, 7 multiplies the first, so the first entry multiplies the first column, and the second entry multiplies the second column. So 7 times 5 minus 3 plus 2 times minus 1 and 2. And what that gives is 35 minus 2. And of course, in order to get the inverse, by the way, a thing that it must not be forgotten is to multiply by so before even doing this matrix, of course, that's already one part of the inverse, but the big part as well is to divide it further by the determinant of it. And the determinant is this times this minus this times this. Alright, so that's 5 times 2, 10 minus this times this plus 3. Alright, minus 3. So it's times 1 over 7, or divided by 7 in other words. Alright, so when taking the inverse, it's important to always also divide by the determinant, which is 5 times 2 minus 3 times minus 1. That's the rule for taking the determinant of a 2x2 matrix. Alright, so now that that is out of the way, I can just move the 1/7 in front and start with what I was doing before. That's this vector by matrix multiplication. So the 7 goes right here, 7 multiplies the first column, and the 2 multiplies the second column, as follows. And what this gives is basically x1, x2 x1, x2 equals 1 over 7 times, and now this can be evaluated. Well, these are constant multiples to those entries inside, so it's basically, it becomes one vector together now, evaluated with numbers, so all add up together. So it's 35, the top ones, plus minus 2, so minus 2, and down it's 7 times minus 3, so minus 21 plus 4, so it's minus 17. Alright, so now I can delete the previous steps, and basically the idea here is that I finally got an explicit expression for x1, x2, which is the result to this linear system, because x1, x2 are the desired values, they are what seek for. So x1, x2, well, 1/7 of this vector, which is 33, and the second entry is minus 17. Alright, so now this can be tested. This can be tested by plugging this back, and of course this is 33/7 and minus 17/7 as follows. This is the result of it. And now it can be tested by plugging it back into the original equation. And what the original equation said is that this vector is the x1, x2, that's the result. So what this basically says is that for this linear system, the x1s that satisfied is 33/7, and then the x2 that satisfies is minus 17/7. Now I can plug it back in, so either plug this value into the x1 and this value into the x2 and see if that all works out, or I can plug it into this matrix equation, and that means that I will write this 2, 1, 3, 5 as this, and then x1, x2 will be this thing, and on the other side is 7, 2. So what this means is, basically I'm writing in the results and seeing if both sides were equal. And deleting all these previous steps to get more space. I'll multiply this out to verify it. So just beware, this is just one entry, this is not two, although it might seem so because it's so wide, it's as wide as this, but these are 4 entries, these are just 2, it's just because these are more complicated numbers. So to multiply it out, the first one multiplies the first column, so it's 33/7 times 2 and 3 like this, and minus 17/7 times this 1 and 5, and that is 66/7 minus 17/7 as follows. That's on the top side, and on the bottom side it is 99/7 minus 85/7. Alright, so these are just two numbers and it has to be simplified. So 60 minus 7 is 49/7 is 7. Alright, and the second one is 99 minus 85 is 14/7, that's 2. So indeed it ends up being that indeed it works out. And this is the expected value because it should be equal to 7, 2. Alright, because this is the 7, 2 values. So indeed this has verified the correctness of this result.